recording. Take it away, Daniel.
Let me begin my story with I'll start with the so-called fundamental theorem of descriptive set theory. Any guesses as to what it is? I mean, it's not a, nobody else calls it. Now that I'm calling it this, what do you think? Throw out. Go.
Countable union of countable Kairos countable still countable.
That is a very important theory, though it's, maybe a little too low level.
Is it just mean by like projections of analytic sets?
No. That's too high level.
Okay.
So most of us have seen this, but allow me to reprove it, so I can emphasize some points. Okay, so what does it state? It says that in some, let's say, complete metric space, separable, okay, or if you want, you can take it to the second countable. It has a countable basis. Okay. Then the countable intersection of open dense sets is dense. From this, there's a lot of things one can say, but for now, I want to draw your attention to just the proof. So what's the proof? I will draw it in R2. But of course, the same proof will work in this side. So we want to, okay, well, first of all, U1 is open dense. Okay. And so in particular, it contains some ball, U1. Okay. Whose diameter is, let's say, less than 1. But U2 is open dense. And so when I intersect it with this open set, it must contain some open ball. So it contains some open ball, B2, where furthermore, okay, we can assume that B2 is contained in this closure, which is contained in B1. We can always do this by starting with our initial ball and then considering the ball of half the radius. We want to make sure that the closure is contained inside of B1. Okay, and then its diameter can be taken to be less than this. And then I can consider, by the same argument, B2 is open, U2 is open, U3 is open dense, and so there must be some further B3, which is contained in U3, where again, you can draw this sort of picture. And the diameter is bounded by it. Then what can you do? Well, you can take a sequence. Okay. X1, let's say X2, X3. And then, so just choose any point inside of B1. And then what can we say about the sequence X1, X2, X3? Well, it gets, contained in smaller balls. Okay, the radii go to 0. And so by completeness, okay, you can conclude that it converges to some x in space X. But furthermore, all of these balls are closed, okay, and the tail of the sequence is contained inside of the ball. For instance, past X3, all of the xi's are going to be contained inside of B3, in particular B3 closure. And so in fact, X is inside of the N closure for all N. And so, in particular, also X is inside of the N for all, and also inside of U N. And this shows that no matter what open set we started with, we can always find a point inside of it, which is contained inside of the intersection of all of the units. Questions about Yeah,
You didn't use separability. Not necessary, right?
yeah, cool.
Separability isn't necessary, right?
Maybe not. I guess the spaces we'll be dealing with anyways. We'll have this problem. But perhaps not.
How do you like the post ball go down the lesson?
Diameter less. Okay. So in particular, we see the structure. So let me make some weird definitions. By the way, the proof I will show you consists of pieces I cobbled together from a bunch of sources. It's possible that some of this are wrong, but still the proofs have something corrected that. So please pay attention to them, right? Yeah. So we see this sort of structure. I'll call it the Baire category theory structure. Another name, maybe you can call it a holding space. It's the following: there's a topological space X, okay, with a basis B that I'm gonna call a hard basis. What does that mean? That means that I forget what everything does. Okay. It means the same thing as basis. So it means that for all u and for all x inside of u, there is some ball, okay, inside of the basis B, which contains x. And furthermore, I want B closure to interface be contained inside of U. That's the shell, okay, of B. So that's where the hard comes from. And then I'm going to say that it has, and I'm going to ask that there is a gradient on it, which corresponds intuitively to this notion of diameter. So I'm going to have B1 containing B2, containing B3, goes forth all the way down, where all of these, each one, is a hard basis. Each one's a hard basis. So that every time I have the following structure, B1 contained in B2, contained in B2. This converges to exactly one point.
So I think again, but in the proof of the category theorem, what does having this sequence conversion to X tell you?
Well, it gives me a point that is in all of the UN. So X is in maybe okay. There's a larger open W.
Yeah.
W intersection.
Well, but when you say the intersection of the open dense is dense, they doesn't think that there's a point in all of them doesn't tell you that it's.
Well,
Okay,
okay.
no, it's open set W though.
Yeah,
W
I should have started with an open set W.
Oh,
So let W be arbitrary.
But
Then I can perform this procedure and find the point.
Okay, I think I missed the implicit.
I forgot to say it.
Yes.
Yeah, my bad. Okay. And this such a property is always guaranteed if we have, for instance, a separable complete matrix. Just take the you can just take these curly B's to be exactly the balls of diameter less than or equal to 1 over the parameter. Right. So example. If X, that's really bad. As X is second countable, completely metrizable, then if you take Bn to be all balls B with the dense set Dn with radii, I'll say M, where M is greater than O. then this satisfies this goal. Okay, and the point of defining this is exactly what is needed in the Baire category. So this is in some sense this is all the structure that descriptive set theory requires us. All the stuff about metrics, it's all fluff. Okay, all that matters is this idea that we have we can zoom it in. That's all that matters. Okay, now let's get to the meat. I guess before I do this, I want to introduce.
Does the V1, V2, V3, are those bases or are they elements?
The curly B's are collections of sets. So these are bases. They are
Right.
Each one is a part basis. Okay.
Yes.
And these B's are elements of the curly version. Yeah.
Is that first parameter the B like a confident subset or something you're waiting?
This one?
Yeah. Like E of something common one over N.
Yeah. Bn is an element of the dense set.
Okay.
The countable dense set.
Yeah.
So you're running the bases of countable?
Yeah. Oh,
Well, you didn't make it.
yeah, sure. Thank you.
But a part basis is just a basis.
Yeah, it is a basis, but in particular, you have this this closure property. That's the only difference.
It's just a basis in like, what is it, like T2 spaces? Or
Yeah, who
something?
cares, right? All that matters is you have these walls that are inside the other guys. That's all that matters. One more example. I titled this talk "One Space to Rule Them All." This is the space. This is their space, which is the space of all sequences n1, n2, etc. Okay, infinite sequences of natural numbers. And what is the holding structure? Okay, the BCP structure on this. Well, B of L, let's say, will consist of all sets of the form n1, n2, dot 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 dot, n greater than or equal to L, star, 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 star. What on earth does all this notation do? So example of the notation. When I write, for instance, 1, 2 star, okay, this refers to the set of all things that look like this. So this is the set of all triples, 1, 2, n, where n is then n. Okay. And so this is the set of all things that have an initial segment n1, n2, dot, dot, all the way to n whose length is greater than or equal to L, and the rest are arbitrary. Okay, so this denotes a basic open of, or in fact, a basic clopin of this this set, and it satisfies these properties. Okay, let's prove something if we first start with definition. The definition 1, I consider a function which I'm going to call code. Okay. X here is the holding space. Okay. So it has that structure. And I can define the following function of code from X to Baire space. I follow them. I'm pretty sure this thing will end up being a conjecture. It's defined to be X maps to n1, which is the minimum n, such that X is inside of Bn, and Bn is furthermore inside of B1. Maybe I'll call it like so. And then n2 is going to be the minimum element, so that X is inside of Bn2, okay, whose closure is inside of Bn1. And I continue in this way. Okay. So basically, this holding structure on X allows us to pinpoint all the elements of the space. Okay. Each element of the space X has its own unique address. right? Here is the recipe of how to get there. This is the instruction.
What are the like not script B's, the B1, B? It's just like there is like for every point there is.
For all B1 in B1 containing B2 in B2 such that the closure
Okay,
is
well, for all sequences, this converges to a point.
Yeah.
I see. Sorry.
okay. I keep not writing everything. That's my does this coding idea make sense? Right. And you can read it too. There will soon be a decoding function, and the decoding function is just well, okay, fine. I'll define the decoding. Definition of 3. Okay. Decode from some subset of Baire space, okay, to, and this is you take in a string. Okay, so S is a sequence, an infinite sequence of natural numbers. Okay, and you map this to the unique X, which is in the intersection of all of them. This is the decoding function. Given every X, I can encode it as a sequence, and the sequence tells you exactly how to drive to X, right? You just zoom into the ball B n sub 1, and then zoom into ball B n sub 2, and so it tells you exactly how to get that. Definition 2, of course, I have to fill in what the blank is. So not all sequences, this will make sense, okay? It needs to be a very specific type of sequence, namely one so that this property holds. So I'm going to define legal string, which depends on X. Okay, this is a subset of n to the n, which is defined as all S's inside of n to the n, so that B of S2 is closed inside of B of S1, B of S3 is closed inside of B of S2, and so on. Okay. So for anytime you have this situation, then this decoding function will converge to a unique point by this axiom. And then the decode function is a map from legal string. And in fact, it's surjective. Yes, it's surjective by the basis. Okay, questions about these definitions? Okay. Intuitively, they're all very computable. Okay, so I maybe it's biased, but in my imagination, when I see this decode, I get the feeling that if you give me a string, you feed me a string S, then I can find X. It feels like I can compute it. It's an algorithm. And one way to formalize this is by saying that all of these things are Borel. What does Borel mean? For the purposes of this, you should think of Borel as countable unions or intersections of basis opens. Or complements can be mixed in as well. That will actually suffice for most people. Of course, if you've done the measures theory, you know that there's some algebra stuff, but what matters is writing this expression. So let's prove it. Proposition 1. Code is a Borel function. So what does it mean to be a Borel function? It means that the inverse image. So we want the inverse image, code inverse of every basic open inside of this to be Borel. So what's the basic open? That's exactly n1 nl star 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 star. That's so I want to show that this thing is going to be some expression like this. Okay. Well, X is inside of here. First, let's do some. Let's not write in things in terms of sets. Let's figure out what does it mean for X to be inside of it. What does it mean for X to be inside of it? Well, it means that so X is inside of here if and only if X has to be in Bn1, right? That's definitely part of it. But furthermore, it cannot be in anything before n1. So in fact, for all n less than n1, okay, X is not in Bn. So this has to be true, and this has to be true, and it has to be true that all the rest of the conditions look like it. So n less than n2, it has to be. All right, let me define some notation. N of n. Okay, sorry. This is the set of all I'll do n of n1. It's the set of all n in the natural numbers, so that Bn closure is contained inside of Bn1. I can specialize this, for example, n2 of n1. I define to be the set of all n inside of n, so that Bn is inside of curly B2. Okay, so it's in the second level. This is sort of the level. The second level of my grading. Okay. And Bn closure is inside of Bn. So this is just all of the set of things that can follow it in a sequence. That's all it is. So let's continue writing this. This is for all n less than for all n inside of n2 up to 1. Okay, where n is less than n2, then X cannot be in Bn. This is the minimality condition. Okay, and of course X has to be inside of Bn2, and so forth. Okay, so think of this as a little algorithm, right? X is inside of this if and only if it passes each one of these checks, which is exactly what you see when you look at the definition. Right? It just passes it. It actually is the minimum thing here, and it actually is the minimum thing here. Questions about
So is it going to be a finite intersection?
In this case it will be. But in general it doesn't have to be. So in fact, what we showed that code inverse of n1 NL star 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 is precisely equal to exactly what the logic tells us. You just read it and then turn it into set theorem. This is the intersection over all n inside of n1, where n1 is the set of it's everybody whose ball is in the first level. Okay, where n is less than n1. The negation of the n intersection Bn1, etc., etc. And this is a finite intersection, in fact, of basis opens and the basic open. No, basic open. Questions about this proposition one? Yeah.
So when we're defining like the code function,
Yeah.
Where does the grading of the basis go? Is that anything you have to do with?
Yeah, the grading is the n1 has to correspond with a ball inside of capital, inside of curly B1. N2 has to be a ball inside of curly B2. I neglected to mention this.
And the n is just like an enumeration of B1.
Yeah, so B1 dot is an enumeration of B1, which is the big basis. Okay? Everybody else is a subset. But the whole point is to describe what chain of things leads to you. And of course, there could be many chains that lead to you. And I'm just choosing the minimum one just so I have a unique. Yeah. Okay. We're good on proposition 1.
Wait, wasn't N1 just at all of the natural numbers?
Yeah.
B1. Okay, sure.
Okay. And then proposition 2 is to show that the set of legal strings is Borel. legal strings is Borel. A Borel subset of n to the n. Are people interested in this? Or do people believe me? It's really quite similar to you know, the thing I just erased, right? You just have to check that each thing does behaves exactly the way we put it to. I'll leave it at that. Proposition 3 is that decode is broken. Decode is broken. This is actually where we must make one edit to our definition. Yes.
Is it rho the same as its graphing 7?
Yes, but this is a non-trivial. Okay. Proposition 3, decode is a Borel function. Okay. Well, what does it mean for decode has to be inside of decode inverse like B sub n? What does that mean? Well, what is that? So, this is the same thing as decode of S is inside of Dn. So S describes some procedure of shrinking the ball, right? Yes.
So does that mean that on the, if you think of like Baire space as like a tree, big tree, means that in the nth, at the nth level of the tree, you take the nth row, or sorry.
Yeah, this Bn is a subset of X. So, yeah, so this picture is an X, and here is Bn, and this S describes the procedure of like pinpointing or honing in on a point. And what does it mean for the decode of S, which is the unique point in the center of all the balls, the center of all the balls, to be inside of Bn? This is where I will make one edit to the definition and ask that actually, and furthermore, for all such sequences that converge to X, they form a neighborhood basis. Or I guess it forms a neighborhood basis of X, which I'm pretty sure means that for all of you containing X, okay, eventually I will get U contains some Bn in this chain. Okay. So for all the chains that converge to X, then so fix U, fix a point X and fix a point U. Then for all the things converging to X, then eventually all of my guys will be inside of U. Okay. That's the extra condition here. I actually don't know if this is equivalent or not to this one. Open question. So assuming this property, then actually a finite portion of S is enough to just to see that decode of S is inside of Bn. So this is the same thing as BS1 is inside of Bn, or BS2 is inside of Bn. You could in fact put closures and everything. Or BS3 is inside of Bn. If you do end up inside of Bn, then at some point the closure of the third ball and the fourth ball must already be inside of.
Wait, is Bn one of your basis elements?
Yeah, Bn is a basis set inside of X.
Yeah.
But it could have been open. It could have just been an open set.
Yeah, if Bn is like the jth guy in the ith grade.
Continue.
So if Bn is the j and the ith gradient, then
Yeah.
isn't the pre-image just the set star 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 j star 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 star?
Not necessarily, because there could be other there could be other chains converging to a point inside. It doesn't have to go through that Bn, right? You could,
Right, it has to be the small.
you could just like skip Bn altogether and go to something. That's totally allowed. Okay, but the point is, now that I've written out this way, then you see that this is equivalent to S is inside of N1 of N star 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 star. Okay, what the hell does that mean? That means it's the union of all N inside of N1 of, I guess, N inside of N1 of N of N star 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 star. Okay. And this is and that's this line. The next line you just write something. Okay. But in fact, decode is a continuous function. It's a continuous surjection from legal strings to X. Okay. The intuition is that if you want to know a finite amount of precision over here, it suffices to have a finite amount of precision over here. Okay. So the intuition is finite precision near X to achieve finite precision near X suffices to know finite string of this. That's the okay. We're actually really close. We've already done something very non-trivial. We've shown that every Honing space. Okay, so in particular, second countable, completely metrizable. Okay, implies the Honing property, right? Even with this addendum, even with the addendum. And so, by the way, these things are called Polish spaces, named after the proof of study. What we've proven is that actually we have a bi-Borel map. Okay, so we've proven that for all Honing spaces X go this way, injection code to the image code of X. I might have jumped the gun a little. Well, we're almost done proving decode. Code is Borel, decode is Borel. Okay. And if we prove that code of X is Borel, a Borel subset of n to the n, then we will have shown that all these very abstract topological spaces are Borel isomorphic to a Borel subset of Baire space.
Okay, go to that.
The image.
Is that not what we defined legal? No, legal stream was slightly different. Okay.
Yeah, legal string was something that definitely contains code of X, right?
I see. Yes. Okay.
So I call this we've almost proved. Okay. The cheap Borel isomorphism. But it's also keep.
Like other coding spaces where code is not continuous.
Code is not continuous.
You said decode is continuous.
Yeah.
So is it possible that every coding space is homeomorphic to a Borel subset of the first space?
I think this guy is really fractal. So I'm pretty sure that you cannot map continuously from
Just to prove out.
the real line, for instance, to just the tree.
I'm curious, like, doesn't the argument work in the other way? Like,
I mean, that one has a bunch of clopin sets.
Yeah.
So I think we.
Yeah, no, exactly.
Kind of
Anything connected.
Yeah.
Right. Yeah, anything connected would be constant. Yeah.
no.
So we're almost done proving something extremely non-trivial. And then this this is the rationale behind why I titled the talk "One Space to Rule Them All." Okay, so we see that Baire space is in fact extremely central to this entire subject. In fact, this notion of this, this holding structure, has this natural number, tree structure baked into it, right? Yeah, so I think I've more than justified the title. Yeah, let's prove that the proposition code X is Borel. Is a Borel subset of n. Okay. I actually got stuck on this for a while, and there is the sort of classical set theorist way of doing this, okay, or the maybe an analyst way of doing this, okay, which I'll just sketch out for you, and then I'll show you the more computationally minded way of doing it. Okay, I want to emphasize that I think with this sort of framework, you sort of see the algorithmic nature of descriptive system. But let me develop the details here. So S is the code of X, if and only if S is inside a legal string. That's definitely necessary, okay. And the code of decode of S is equal to S. Okay. So already from an algorithmic point of view, we're pretty sure that code X is Borel. Okay. How do we determine membership of code X? Well, you give me S, okay, and then I determine I run a little machine to tell me yes or no, is it in legal string? But this machine is good because legal string is a Borel set. Okay. Then I run two Borel functions. Okay. You give me S, I run decode, which is Borel, so it's good. Okay, it's computable. Then I run code, which is computable, and I test equality, which is definitely computable. Okay. So just from an intuitive sense, you should believe me that code of X is Borel. But we should write out some formulas. So how is proof one? Proof one. Consider H defined to be code of decode. Code of decode, which is a map from legal string to itself. Okay. And then consider the function graph, which is the map from legal string, I'll just call it ls, to ls squared. Okay, which maps y to y comma h of y. Okay, so this is the graph of this h. Okay. Then this guy is equal to graph inverse of the diagonal. Do you believe me? Okay. And the diagonal is a very Borel set. Okay. Graph is a very Borel set because all of these things are Borel. So you can call a day and be like, yeah, this we're good. So S is in S. So S is in the set if and only if S is in this Borel set and in this Borel set. I really didn't like this. I feel like it should reflect this idea that it's computable. So let's try to think about it that way. Everybody good to say goodbye? Proof one. Proof. Well, S is inside of code inverse of S, and then decode inverse of that. Okay, that's this expression. If and only if, for all n, S inside of Bn, let me call it beta n. This is a basis element of Baire space. In other words, I'm saying that if S it looks like n1, nl, star. Okay. if S looks like this, then S had better be inside of D code inverse of code inverse of beta n. Okay. So in other words, let me write it this way. This is equal to D code inverse of code inverse of the intersection over all L of S1 through SL star star star. Yeah, because this intersection is equal to the singleton set. And this is just a way to formalize how to refer to S1 through SL. Okay. Otherwise, I would be referring to myself inside of this description, which is legal. But fortunately, in logic, we're very used to figuring out ways to stop you from referencing yourself through hacks like this. So through hacks like this, I convert this idea into this. Okay. And then this logical formula can be turned into precisely so. This is exactly equal to S inside of the intersection over all n of negation of Bn or this two. And this is Borel. So there are two proofs. You can look at the graph inverse of the diagonal, or you can think like a logician and look for ways to stop referencing yourself in your formula. So that with the proof of proposition 4, we have actually achieved the cheap Borel isomorphism. Okay, this is good, but we're here for the Borel isomorphism theorem, not the cheap one. So let's keep going. Well, okay, so part 3. I might have missed some parts here, but this is part 3. So for now, let's assume as a black box that, well, okay. Before I say this, where are we at? We want to show that all Borel subsets are Borel isomorphic to, let's say, n to the n. In fact, all coding spaces are Borel isomorphic to, let's say, n to the n. We've already achieved Borel isomorphism to a subset, a Borel subset of n to the n. So now all we have to think about are subsets of n to the n. So we've golfed our way down from an abstract X to subsets of Baire space. This is an improvement. Okay, so
be careful about not any subset, but a subset that contains an open set or something.
No.
There are points in.
Sorry. Well, all uncountable.
Okay. Something.
Indeed. Indeed. Countable ones are Borel isomorphic to the natural numbers or subsets thereof.
Cool.
Okay. Let's see. So let's take as black box for now. I'll maybe say a couple words about this black box later. All Borel subsets of all uncountable Borel subsets at the end have an embedding of Cantor space, which is 2 to the n. Okay, so all infinite strings of bits 0 and 1. Okay. I'll mention some words about this here in a minute. But assuming this, here's some proposition 5. Consider, well, okay, let me say the goal. We have 2 to the n, and by this theorem, there is in fact a continuous. continuous bijection, well, injection, bijection to the image of this Borel subset, which I'll call E. Okay. And this obviously has an inclusion into n again. Obviously, so what I'll show is that there's actually a bi-Borel inclusion from this to this. Okay, this I'll call U. Okay. This is very explicit, and in this way, I will have sandwiched E between two inclusions. Okay, and so if you remember something called the Cantor-Schroeder-Bernstein theorem from set theory, if you have an injection into this way, an injection this way, then you can do the zigzag argument to show that there is actually a bijection. In fact, because everybody here is Borel, the thing you cook out from Cantor-Schroeder-Bernstein will in fact be a Borel isomorphism. I will maybe sketch the proof of Schroeder-Bernstein as well, but for now, let me tell you about U. Proposition 5. U a map from n to n into 2 to n. I define as follows. Okay. U is for unary vector. If we had more time, I would encourage you to think about a map display. But I'll just give it to you. Okay. Intuitively, it seems a little crazy, right? This side is much bigger than this side. But infinity is weird. So here's the map. So n1, n2, dot, dot, dot. I just map this to 1 with length n1, okay, 0, 1 with length n2, 0, and so forth. Okay. And clearly this is an injective function, okay, the inverse is followable. So for I claim that this is a continuous function. Well, if I want a finite amount of precision over here, indeed, all I need is a finite amount of precision over here, right? If you tell me I want to see this, well, then I can tell you exactly what you need to put in here to see that string pop up. Of course, you can formalize this by analyzing inverse images of this thing with a star at the end, but I'll brush that under the rug. Part I, the image is Borel. What is the image? What is the image? It turns out to be strings S that start with 1. It has to start with 1. Doesn't. Just kidding, it doesn't.
Are you starting your natural numbers at 0?
Yes, of course.
Okay.
What do you take me for? Yeah. Okay. So it's perfectly allowed that it doesn't start with 0, but furthermore, there must be infinitely many zeros. This is the only restriction. Okay. If there's infinitely many zeros, then that must have been in the image of such a map. The only issue is if there's infinitely many ones, in which case it could not have been the image. It could not have been an image. But of course, this is very Borel. Okay, you can exercise. Write down this as a countable intersection code. Yeah, or something like this. Yes. Some scrunched eyebrows.
I just know you said that infinitely ones is a problem. That's just fine. Like we knew like
If it's all ones is an issue.
All ones.
If it's all ones,
Finitely many zeros is an issue.
Yeah, maybe just misspoke because you said infinitely ones is an issue, but that's if you just do like
yes, right. Yeah, you're right. You're right.
All
The tail of all ones is
Yes,
equal.
yes, yes.
That's right. Yeah. Okay, this is Borel stuff. Good, great. And then finally, the inverse function. The inverse we can define as V from the image of U to n to the n, which is just read the string and then just smoosh it all together. Okay, this is obviously also Borel. Oh, in fact, it's continuous. Okay. Yeah, actually, it's fine. If it's not continuous, it's sure it's not Borel. I'm pretty sure it's continuous. Okay.
This is very
Good. So we now have this sort of picture, right? And so the only two remaining steps now are this Cantor-Schroeder-Bernstein thing I mentioned, and then this black box that I have. Which non-zero. Okay, let's do. So two remaining. And then we're actually prove the whole theorem. So I need a Borel version of Cantor-Schroeder-Bernstein. And then I need this black box. Those are the two remaining pieces. Okay. So what's Cantor-Schroeder-Bernstein? It's too good of an argument not to share it. So if you've seen it before, now you see it again. I have x here, I have y here. F is an injective function. G is an injective function going this way. Okay? And they're both bi-Borel. What does it mean to be bi-Borel? It means that you are Borel and your inverse, which is defined on your image, is a Borel. So you need to be Borel in both ways. Otherwise, it doesn't. Okay, so what's the situation? I finally get to use some code. Well, take all of y, okay, and map it by G. Okay, it's going to be some subset of X. Okay, so I'm going to draw the subset as this. Suppose it looks like this. So this is G of y, which I'm going to call Z1. Okay, this is G of y. And I'm going to call this the remaining piece, which is everybody outside of the image of G, to be A1. A1. Okay, now what do? A1 maps to some set F of A1. Okay, it maps to some set A1. And this set is a Borel isomorphism. It's a restriction of this onto this, and it's an Borel both ways bijective. Okay. Great. Then what do? Well, I just look at the remaining piece, okay, which I'll call like B1. Maybe I won't call B1, maybe I'll call B2. And then I'll map it to somewhere over here. Right? There'll be a subset of the remaining spot. Okay. And this is this is G of B2, which I'm going to call Z2. And of course, there may be some stuff remaining, but that's fine. I'll just call it A2. And that is bi-Borel to some at A2 here. And I just continue. What do I get when I continue? I get an onion A, okay, which is made up of a bunch of A1 through A2, right? It's like layered. And then I get a bunch of F of A1, F of A2. So this whole thing is F of A. And of course, there might be some stuff remaining. But I'll just call whatever is remaining B. Okay. And B was the intersection of all the BNs. It's all the BNs, as you can see from the picture, right? It's the intersection of all the BNs. And this here, by definition, is the complement of A. So this complement of A, which is the union of all the ZNs.
Yes.
The intersection of all the Z's. This is the intersection of all the ZNs. But I claim that this thing, that G of B, is equal to this. So in other words, G is a bi-Borel map from this bottom chunk to this bottom chunk. And F was, of course, a bi-Borel map from this top chunk to this top. So we're all good. Okay. And all that remains is a little bit of manipulation. So this is the G applied to the intersection of B and N, okay, over here. But because we're working with injections, This is GB of n. This thing is by definition equal to instead. Okay, so analyze this crisscross picture in a little more detail. Get used to my notation of A's, B's, and C's, okay, and then the rest will be clear. Yeah.
So on the A part here, so you're trying to find a bilateral map from X to Y. And so like on the A part you just do F, and on the rest of it you just do G. Well, that's fine. On this part down here you do G. That's very different. So like, is there anything you have to show that you sort of like paste into Borel maps that they're Wiener is also Borel?
It's fine because phi Borel means that the inverse image of every Borel is Borel, the forward image of every Borel. And that same thing is true here. I just take any set here, I chop it into this set is Borel.
Oh.
Because of all this phi Borels. And then
So because A is from
yeah, so this is literally the original proof of Cantor Schroeder reverse type, except I just smacked the word Borel like 4 dozen times. And all of the relevant okay, so that's the last piece. Sorry, the second last piece, and then finally, what do I have to say about this black box? Here I will do the classic sigma algebra trickery. Okay. I will show that I will show that the class of subsets of n to the n such that there exists a continuous map contains all of these. Contains all closed subsets. Okay, contains all closed and is closed under both of these operations. Okay, and this is actually the only part of the argument in which I have to use the full definition of what Borel knows. Before it suffices to work with these sort of finite layers of intersections and unions. But actually, in this part, it is the only part where I require the full use of this sigma algebra trickery. Most of these pieces are easy. Okay, most of these pieces are easy. And the only bits that require some work are this one. And how much time do I have? Okay. We'll call it a mystery. Come talk to me after if you're interested. But this is basically the full. Any questions?
every compact room space.
I don't know. Probably. Well, okay. In fact, every Honing space is bi Borel to Baire space, which is bi Borel to Baire space.
Yeah.
If you're interested in homeomorphism, that's a much more complicated. But the point of this theorem is to say, yeah.
But they're not.
Yeah, exactly.
So let's
Yeah. Well, you can ask what
We're gonna have to go with the standard space. Oh, for this
that's true.
Yeah, sure. That's gonna be massive.
Yeah.
There's like quantification you can do, right? Borel means the inverse image of Borel is Borel. Continuous means the inverse image of open is open. And you can consider like what is the inverse image of a delta set? Is that
Yeah, bro,
layers up in the
hierarchy or whatever nonsense.
And then descriptive sector has studied this hierarchy to death, and very technical results have been achieved. Yeah. But the whole point of the theorem is that there's actually only one space in the Borel category, or in the uncountable Borel category. Every space is the same. Okay.
Basically, why is this back to this like blue add-on here
Yeah.
to our coding space definition?
Yeah.
Do we not get this for free?
I'm not sure.
It should be true.
Okay.
Oh, really?
Yeah,
Yeah,
see, like,
you
X
just
is gonna-
intersect all of your like B2 could be B1 intersect all like intersect
Kind of
with itself.
example.
Like you just you countably index your things that intersect to like countably. I think you can be able to write it without finding it.
It's even more.
Okay, maybe I'm wrong.
For example.
Oh, what's the trivial
The
count?
trivial count, for example, is you take your metric space at like R2, like R or whatever. And then you give it, and you give it the discrete topology. And then to all of your grading, to your basis, you add one open set, which is just that one point. So it's the set of things with radius.
That's not gonna be countable.
No. But your basis is still gonna be countable because it's still it's still going to be like, it's your whatever your old basis.
So what is your basis? It's
Oh, well, the old basis was countable, right? So I'm gonna assume that.
Yeah.
And then I'm just adding 1.1 open set to it. Oh, I see that's not countable. Okay.
like it should be. You actually should be able to write B2 is B1. Like take an element of B1, intersect it with every other element of B1, and then union that over all of B1. So it's a set of two intersections of open sets. B3 is the set of three way intersections.
But
The
B1
end.
is everybody.
Yeah, so we had to start adding things.
No.
Oh, so you want inclusion. Okay, I'm getting rid of inclusion.
Yeah.
I mean,
think
you could just union after I do this. You could do this. No, you can't.
No.
Dang
Someone asked me about this. I want to.
But I have a question. Why isn't code continuous? Because
Because there are very few continuous functions from X into Kemper's from X into a totally disconnected space.
okay, but I guess what I was curious is, say I move my point in my metric space by only a very small amount epsilon.
Yeah.
Surely, like what?
No. If you move your point by a very small amount, the tree you go down completely splits apart.
Why?
Because that's sort of the precision, like your epsilon is.
Yeah, because of Hausdorff's this.
Yeah.
You have 2 points and you have a ball here and a ball here.
No, but surely like the B1s.
Then you separate.
No,
You're not like
but like I'm thinking of like the B1s are like the balls of radius 1. So surely if I move my point epsilon, it's still the same ball. Like I hone in. I start with big open sets, and if my point has only moved a little bit epsilon, I'm surely still using the same big open sets until some finite number ends. But I can choose epsilon depending on n. Like so, surely the first part of the string should be the same. I'm confused. I'm confused.
I think you're right, you'll still lie in the same ball, but you may lie in a smaller ball, right? You may lie in an earlier one by just moving a tiny bit, right?
I don't know. Something must be wrong with your argument because it cannot be true. The result it cannot be.
It's just not true. Well, that's the same, like if X is like the real numbers, then any that the real numbers to their space constant. So sometimes code would be a constant.
Yeah. Okay, I accept that point. I just don't see why, like, surely to be continuous, I need to prove that, like, okay, it's fine.
Exercise. Any remaining questions?
Those I have two polling spaces.
Yeah.
So this tells me that there's a Borel
I smart.
is there an algorithm because like suppose that these are like reasonably nice home spaces. So, are there any cases where I can say there's a theorem that gives me an algorithm say what is the complexity of the simplest Borel?
Yeah, I think you should have PhD and I'm sure people have studied. There are notions of what's called a computable Polish space. And they talk about exactly this. Yeah, also open question by the way. I don't know if coding space implies Polish. Like, are they actually the same notion? I'm not entirely sure.
What? I'm sure. Yeah. What's the definition of home space? Home space.
So, like, from this structure, can you call up a complete metric?
Can we go remember what's my Aristotle was say?
There's like the Alexandrov metricism.
No, I mean like if you have your grading, can I just specify?
Maybe.
Like
Does it satisfy the trembling?
if a subspace of a Borel space is that a Borel subset of a Borel space only?
I don't know. No, I don't. But that's inclusion. Like, holding is topology. Topology is fake. All that matters is Borel structure. That's
All right, let's thank the speaker.
It's feedback form.
I'm genuinely confused. I think I got something for you.